Hello, welcome back to the course on remote sensing GIS and image processing in urban infrastructure management. Today we are going to look at a case study that is urban growth modeling. These are the topics covered in today's class: model theory and background, data requirements, preparation, naming convention for the model to execute, and we also discuss how to use open source data and setting up of the model, that is SLEUTH. We are going to study about SLEUTH today along with Sigwin interface, and how to access SLEUTH data from project Gigalopolis, that is the main website. And we'll also understand what is the SLEUTH folder structure, what does different folder mean, etc. And finally we will see different commands in Sigwin interface also. And then we have something called a scenario file, which is the backbone of SLEUTH. And calibration phase, we will understand how the calibration takes place of the model. And finally we will see model outputs and sample results. So why do we need modeling, urban growth modeling? The basic question is that. So as we can see, the global population is continuously rising, and also we have urban growth surge in major of the cities. And it is no longer a city. If you can see in this particular figure here, there is a ribbon kind of growth, meaning there is a gap, there is a bridge between two different cities, that is called as a ribbon growth, and this is also known as corridor. When it comes to urban centers, it is called as urban corridors. So throughout the world there are several major corridors. However, in India, if you see, there are 7 important urban growth corridors, that is Delhi region, Mumbai Ahmedabad, Mumbai Pune infrastructure corridor, Chennai Bangalore Mumbai corridor, Bangalore Mysore corridor, Mumbai Jalgaon corridor, and Hyderabad Vijayawada corridor. So these are the basic corridors which have been identified by the government for the growth in the next decade. So there is a need to understand urban growth, how it grows in the future. To know that, we have various types of urban growth models. This is broadly divided into 5 different categories. The first one is artificial life. Second one is intelligent stochastic optimization process, wherein the entire algorithm depends upon the optimization technique, such as genetic algorithm or particle swarm or simulated annealing, etc. Then we have evolution computing and spatial DNA. This is nothing but it is based on artificial neural network. Neural nets have a major role to play here, and also called as spatial DNA. And the fourth category is knowledge based intelligence system, wherein we have fuzzy logic, expert system, heuristic search, and reasoning system. The last one is hybrid AI system. Any of these two category can be merged together to get a output. So that is called as hybrid AI system. Today we are going to focus mainly on cellular automata modeling, that is cellular automata and Markov chains, and then we also look at SLEUTH genetic algorithm models. So the literature suggests that the final outcome of model are to understand the complex interrelationships between natural ecosystem and an urban environment by observing the irreversible heterogeneous pattern of change. What does this mean? That means basically we are going to understand the natural setting versus the urban setting and how these both are interacting in today's real world scenario. So as you all know, urbanization is an irreversible process, meaning to say once the urbanization takes place, it cannot go back to the original state. We cannot go and create a natural water body which is closed, and if we build something on that water body, that is it, that is the final thing, and we cannot go back. So that is why we call it as irreversible process. And the research gap identified is models have been adopted to predict future urban growth using simple transition rules. That means if today some part of the land, if today it is a barren land, then let us say we are going to give the rule as that barren land can be changed into urban land. So that is a very simple transition rule. Markov chains are spatially non-explicit because they compute only the probabilities of land use transitions, and when it comes to traditional approach, it fails to understand and predict complex urban patterns. What we are seeing today is very complex urban pattern. Earlier they used to have big town mega plans or city level mega plans, and those plans were working out really well. But in today's scenario, the planning has entirely failed. As the best example you can see is the floods, whether it is in recent Jaipur floods, or it may be Mumbai flood, or it can be Chennai flood. So why does this happen? This is basically happening due to the failure in urban planning. So why does this plan fail? Because we are unable to understand the complex urban patterns. So how do we understand complex urban pattern? Using very sophisticated urban growth models, we can definitely come up with realistic solutions. So the significance of artificial intelligence and stochastic optimization is given more importance here, and its deep theoretical understanding for urbanization is the need of the hour. So that is why we are going to model the urban growth with respect to these factors. Let us understand what is cellular automata and why we need cellular automata. What is the best other alternative as well. It is basically it is operationally very simple by generating dynamics that can reproduce traditional process of changes, and it can generate very complex forms also based on the user and user's requirement with the help of very minimal transition rules or very simple transition rules. Transition rules means you can tell a rule if the cell was 1 before, and all the cells will be in the form of binary systems, that is 1 and 0. 1 meaning to say urban, 0 meaning to say non-urban. So a simple rule is whatever was 0 in the previous year, let us say it becomes 1 in this year. So that is a simple rule. So if you do like that, all the cells which are having non-urban values will become urban in this year. That is a very simple rule. But it is complex when other entities also comes into play. For example, there is water body. For example, there is forest region. So you cannot say it is only urban versus non-urban. There are so many factors that affects urbanization. So for detailed modeling, it would be advantageous to integrate cellular automata with various GIS modeling techniques. And cellular automata is capable of exploiting fine-grained spatial information. That means whatever the data you are getting for free today from Landsat is 30-meter resolution. You can also include 5-meter resolution. You can also include 1-meter resolution in that. So CA gives realistic urban patterns. Let us understand what are the different basic building structure of CA. Cellular automata is basically a two-dimensional dynamic system in which local interaction among component, it produces global changes. That means a very simple rule in the input can change the output drastically. So you need to remember this: local interaction can cause global reactions in time and space. So if you see the equation of cellular automata, each cell state is defined by S, okay, or each automation is defined by S, and the future state of a cell, that is t plus 1, is equal to, that means it is dependent upon, or it is a function of, that is f of st, that is cell state at time t, that is at present, and n is nothing but neighborhood, and t is nothing but transition rules. So the cell state in future t plus 1 directly depends upon the cell state that is today and upon the neighborhood of the cell and the time, okay, or the transition rules. So cell is, these are the basic element. Obviously the cell is a basic element of cellular automation. It behaves like a memory unit. It stores only binary values, as I mentioned. It can be 0 or 1. And lattice is something, when a group of cells are together, it is called as a lattice. Rules, cells in lattice represent static state. Okay, if you want to introduce dynamic system there, you need to have certain transition rules. And then the last one is neighborhood. Neighborhood means if you take a principal cell, the surrounding cells are called as neighborhood. It may be in the form of plus shape, or it may be in the form of a square shape, anything like that. So generally we use two very popular neighborhood, that is von Neumann and Murray neighborhood. If you combine these two neighborhood, it becomes extended von Neumann neighborhood. Then coming to the SLEUTH model, SLEUTH is an urban growth model. It is definitely based on cellular automata. So it stands for, the abbreviation of SLEUTH stands for slope, land use, exclusion, urban, transportation, and hillshade. So these are the 6 different layers which are used in sleuth modeling. This was initially developed by Casey Clarke. He is a professor in UCSB, and the model, its documentation and source code is publicly available. That means what? This entire model is free of cost. You don't have to pay any money, and the biggest advantage is you have the source code with you, so that you can alter the source code as per your requirement and as per your study region. Then sleuth is an outcome of 2 sub-models. The one is Deltatron model, Deltatron land use model. This basically takes care of the cellular automata and the Markov chain part. Then it is coupled with urban growth model, that is Boolean model. So sleuth depends on various parameters and transition rules. Let us understand what are these. Basically, the model depends on 5 different coefficients, or it is also called as parameters. So for each of these coefficients, we have values ranging from 0 to 100. So this 5 coefficient, it completely controls the entire behavior of the model, and these are predetermined by the user at the start of every model run. That means the ultimate aim of our thing is to find out the optimum coefficient value which will be useful for our region to model the future change. These and further, these parameters include diffusion, that is the first parameter or the first coefficient. So then we have breed, spread, slope resistance, and road gravity factor. So diffusion means you might have heard diffused growth. That means if there is one particular pixel here, then there would be some random pixel at a place in another place. So how did that random pixel came? That is by diffusion. It is not connected to the existing pixel. And then we have something called as breed. Breeding means you have 2 particular pixels nearby. There will be one more third pixel coming up in the next time period. So that is called as breeding. Then we have spreading. Spreading is nothing but slowly spreading from the urban core centers. Then we have slope resistance. Usually in hilly area, the slope resistance will be very, very high. And in the normal flat terrains, slope resistance will be very, very less. So slope is also one of the important factor which decides upon the urbanization. And at the last, we have road gravity factor. So as you all know, highways and other major roads, they attract a lot of urban growth. And lastly, we have various rules, that is called as transition rules. As I discussed earlier, cellular automata, the basic thing that simulates is transition rule. So in sleuth, we have 4 inbuilt transition rule. The first one is spontaneous growth. Then we have new spreading growth, edge growth, and road influence growth. Spontaneous growth, as I explained already, this is directly associated with diffusion factor because it is diffuse. Spontaneous means random. Randomly some pixel is coming up. Then if you see the second one, that is new spreading growth, it is the breed factor. You have 2 pixels at 2 different locations. Third pixel is coming to picture because of these 2 pixels breeding. Then third one is edge growth. That means the pixels already surrounding the present urban area, it will start growing with that. So spread factor is associated with edge growth, and also slope resistance is associated with edge growth. The final thing is road influence growth. So here in the picture you can see wherever there is a road, you have high possibility of urbanization taking place, and this is associated with road gravity, slope resistance, and breeding and diffusion. If you compare the cellular automata, traditional modeling, and sleuth have, of course, it has overcome the limitations of cellular automata. For example, in CA model, it is highly dependent on data quality. However, sleuth works good with both fine resolution and coarse resolution data sets. And in cellular automata, you have growth in multiple directions cannot be identified or recognized with ease. But if you take sleuth, the transition rules will take care of all types of growth, and it can identify multiple direction growth, and transition rules are bounded by suitability defined by exclusion and from the slope gradient. This we will understand when we go to the demo. CA captures and controls only spatial dynamics aspect. CA has the potential to capture only spatial part. However, if you want to include the temporal part, that means time period, you have to go for Markov chains. So if you consider sleuth, there is already inbuilt Markov chain in it, so it takes care of both spatial and temporal aspects. And lastly, the Cellular Automata doesn't have any calibration procedure. However, CA based sleuth, we have the calibration in 3 different rigorous phases. Next, we'll understand how to prepare data set for this particular model. This model accepts only grayscale GIF images, that means black and white images. Okay, so you need to have 6 types of grayscale GIF images. So the values of this grayscale image, it can vary anywhere between 0 and 255. 0 means non-existent or null value, and 255 means it is treated as existing or live cell. At least you need 4 time period of urban maps. That means you should have, let us say now we are in 2020, we need to have urban data from 1990, 2000, 2010 and 2020. If you have these 4 time period data, then only you can calibrate and predict for 2030, 2040, 2050, like that. Roads must be represented in 2 or more time periods. That means you should have road, how the road was in a particular city in 1990 and how the road is in 2020. Both this scenario is the bare minimum requirement. Then 2 time land use you need. So this is basically for Deltatron land use modeling, 1990 land use and 2020 land use. Then you need to have GIF images in terms of same projection, same extent and same resolution. This matters a lot. Then how do you get the data? So these data are freely available. We are completely dependent upon open source data sets. Landsat data will be, it can be downloaded from Earth Explorer. It will be helpful in your land use analysis and urban data extraction. And then we have Google Earth. This is basically used for geo correction, classification and validation. More details will be taught to you. I think it is already finished in the theory class. And it will also help in collection of point, line and polygon data. Then boundary maps and raster layers can be taken from city development plan. This is basically to include the excluded map. That means the regions which are restricted for future urban growth. Suppose let us say there is a lake and you don't want to close that lake and build a apartment on that. So that becomes a restricted region, like that. And then we have field data. You can use your GPS to obtain the field data. Slope and hillshade can be obtained from Aster digital elevation model. So how to download Aster digital elevation data and all these things will be taught to you. And lastly, we have transportation data, that is basically the road layers. This can be obtained from Bhuvan. Bhuvan is the Indian version of Google Earth. Please look into the website of Bhuvan. And also we have OpenStreetMap, which gives the all kinds of street data. Then what are the softwares that are required? We can use Google Earth, Bhuvan, Grass GIS can be used. Grass and Quantum GIS, these two are under OSGeo. So Grass is basically used for processing the raster data and vector data, and QGIS is basically for visual interpretation, to manage, edit and play along with your attributes. So you can use these two. Then we have Sigwin, which serves as the base for sleuth model. So this is a large collection of GNU and open source tool. It is basically an open source tool. This also you can have a look. Then finally we have Project Gigalopolis. If you are using sleuth, it is better recommended to visit the Project Gigalopolis website once before you start modeling. So let us understand input data in detail. The term SLEUTH, as I already mentioned, S for slope, L for land use, E for excluded, U for urban, T for transportation and H for hillshade. So S for slope, slope is the derived form of digital elevation model. This we have already covered in our theory class. So what is slope map and how we can derive slope map from them and all these things. So basically here in sleuth model, the cell values must be in terms of percentage and it should not be in terms of degrees. So if you have in degrees, then you can of course convert to percentage. That is not an issue. Then we have pixel range. Pixel range should be varying from 0 to 100. Values which are greater than 100, it should be read as 100 only. And the second layer is land use layer. As I mentioned in the earlier slides, we can use the land use for two different time periods. So here I am using the land use for 1999 and 2017. So each pixel value contained in the grayscale, it will indicate the land use unique category in the land use. So here if you see in this particular land use, we are basically considering four different categories. The first one is urban, which is marked in red. Then we have vegetation, which is marked in green color. Then we have water, which is marked in blue color. And finally we have other land use class, that is in yellow color. So here also the pixel range is 0 to 255. The third layer is excluded, that is E. Locations that are resistant to urbanization, like for example, it may be a lake, and if you want to conserve the lake for your future generations, that can be an excluded region. Or if you want to take any military or any other area, so that can also be a resistant to urbanization. So here areas are considered where urban development is considered impossible in future. For example, water bodies, natural parks, national parks, etc. So these are given a values of 0 to 255. Values greater than 100 can be read as 100 only. So basically this is a binary, that is 0 and 100. 0 means it is completely available for urbanization, and 255 means it can be taken as it is resistant to urbanization. Then the third one is urban layer itself. So here as I mentioned, we need four different time period urban layer. If you can see, 1990 urban is there, 1999, 2009 and 2017. Roughly the time period between each of the image is 9 to 10 years. So it is also binary classification. It indicates only urban versus non-urban, and pixel value is given 0 for non-urban, and any value it can take for urban data. Then the last one is the last but one is transport, that is nothing but the road data. It is similar to your urban data. So here you can see road in 1990, 99, 2009 and 2017. Over the years, how the roads density has been increased. So the pixel value ranges from 0, that is non-road, to 256, that is road. And you can also give weightage for the roads, such as if you have a national highway, you can give the weight as 4, and this can be very high. And if you have state highway, you can give weight as 2, it is medium. And then if you have major district road, you can give the weight as 1, it is low. And finally, if you have no roads, that is no road data, then you can give 0. The last layer is hillshade. So hillshade tool obtains the hypothetical illumination of a surface by determining the illumination values for each cell in a raster. That means if you can see here, you can see shadow in the northeastern part here. So basically what you are assuming is your sun is kept at certain altitude and at certain direction. So these are called as altitude and azimuth values. So wherever you keep the sun, how the shadow is forming, and based on the shadow or lighted area, we are going to determine what is the exact terrain of a particular place. So here in this figure you can see this all layers, whatever you have here, it has more or less flat terrain, and here wherever you can see the rigid part, it has a very rough terrain. So to give further definition to a region, water bodies may also be represented using hillshade map. You can put water bodies on top of this hillshade map, and pixel value can range from 0 to 255. Values more than 1 can be read as 255. Basically here you're going to classify the entire image between 0 and 255. These are the requirements of sleuth model. Next, we are going to see how to set up Cygwin interface. Cygwin, as I already mentioned, it is the interface to monitor Sleuth. So Sleuth is basically, it was developed as a Linux program, and it will not run as program in Windows directly. So we need some common interface. So that is why we are using Cygwin. So if you want to download Cygwin, you can easily download it from this particular website which I have mentioned here. And for running Sleuth, these are some basic commands which is similar to your C programming. For example, if you have pwd, that is print working directory, it will show you in which directory you are currently in. And then cd space e colon, that means change directory to E drive. cd sleuth, that means in E drive it will further go to a folder called sleuth. Cd gd make clean, these are different commands and its uses. We'll discuss it later when we move to the demo part. Then to execute sleuth we have different folders. So here if you can see input, output, scenario, and all these folders are very very important in sleuth. So input folder, it is where you store all your input data sets. um, you can create as many subfolders as you want for various calibration procedures. Then output folder, you can have similar to input. Here you can store all your output in terms of GIF and in terms of Excel results. Then we have scenario folder. So this is like the skeleton of sleuth. So the scenario file act as a basic part of sleuth, without which you cannot execute sleuth. Then we have GD, that is the GIF image directory. So here it contains all the GIF image files. Similar to GD, we have one more folder, that is worldgif. So worldgif supports the GIF image at the background and it will give you the output as required in terms of GIF. Then we have other extension files with .o, .h and .c. .h is header files and .c is C program files. So these are very very important. All these things should be present in your main folder. So I already mentioned the scenario file acts as a skeleton for your sleuth model. So to run any scenario files, you should go first into the scenario directory. Inside scenario directory, you will have a lot of files. This you need to create scenario files. I will tell you how to create that also. And when you give a command, you can give grow.exe and followed by mode. In sleuth there are three different modes. The first one is test mode, and the second one is calibration mode, and the third one is prediction mode. So first what we do is we test the data whether it is working fine or not. Then we give the prediction or the calibration, and then finally we'll give the scenario file name. So the scenario file contains all necessary data to run the model. You can set the parameters. Parameters are nothing but the coefficients. So we discussed in the previous slide, like diffusion, breed, all these things can have different values based on your calibration. That we can set it here. File naming convention should be proper. This naming convention is given in Project Gigalopolis website. It has to be followed on these standards only, otherwise the model will not work. Then you can give the set of coefficient values, log files, etc. Color controls can be managed here, and you can also view the comments. Here if you can see, whatever line is starting with a hash, it is a comment. That means it is giving you some additional information about the file. Okay. So these are various screenshots of scenario file. For example, if I take the first variable, that is path name variable. So here you can specify what is the input directory from where you are going to take the input images, and then you have output directory. It will give the output images, or output images will be stored, and from where you can check the GIF is generating from which, that is nothing but the world GIF, etc. So like this you can also set the various calibration parameters. Here you can see diffusion start 5, diffusion step 1, diffusion stop is 5. That means it will take a single value of diffusion as 5. And similarly you can have any values here ranging from 1 to 100 based on your calibration. So similarly you have values for prediction also, and you can also set the prediction start date and end date. For example, prediction start date can be 2020 and prediction end date can be 2026, something like that. And finally you can set color table settings can also be made in the scenario file. So this is the general sleuth workflow or the structure of sleuth. So initially you will create the layers, spatial data processing happens, data standardization happens. What is data standardization? As we mentioned earlier, sleuth completely runs on GIF dataset, that is the grayscale images. So you cannot randomly give some JPEG or some TIFF image or some shapefile, nothing works. It is only based on pure GIF images. So data standardization, we also see number of columns and rows it should match, and also the resolution. So naming standardization should be followed. And second part is model calibration. So here we have three different calibration, that is coarse calibration, wherein the image input will be 120 meter resolution. Fine calibration, image resolution will be 60 meter resolution. Final calibration, image resolution is to the highest, that is nothing but 30 meter. Then we have parameters, obtaining parameters from this calibration method. The third stage is model prediction. You can have various scenarios to get a scenario feel, like if proper city development plans are implemented, what is the scenario? If we are trying to implement only few parts of the city development plan, the restriction is not so strict, then how it is going to affect? All these kind of scenarios we can monitor. Finally, we can get in the fourth stage model output in terms of statistics. It will be basically in terms of Excel file, or we can also have image output. So during the calibration, as I already mentioned, we have three different calibration, that is coarse, fine and final. So here in the coarse, we have iteration in large increments. We are going to check in the increments of 25 from 1 to 100, and coefficient can be explored in the full range. Okay, but if you see in coarse calibration, the image size is 120 meter, and fine calibration the image size is 60 meter, and final calibration image size is 30 meters. So this is how we run Sleuth with the help of these three calibrations using Monte Carlo iterations. And there is also, how do you validate the model? Once the model is run, how do you understand whether the model is giving you correct values or not? So basically we have, after each run, we can obtain 13 different metrics. These are based on regression values. So to evaluate, basically these are for the evaluation of goodness of fit, how good your modeled output is fitting with your actual data. Out of these 13 metrics, based on the literature, we have chosen 6 important metrics, that is compare. Basically it compares the model versus actual urban layer. Population is the regressed value for actual urban versus the control layers and the modeled urban. Edges, cluster size and least alley. Least alley is very very important. So it is a shape index. Basically it compares the shape of model growth versus the actual growth for whatever control years you have taken. So this is one of the output of calibration phase. So basically it comes as a .txt file. So if you copy the entire content of .txt and put it in Excel, this is how it is going to look. So here you have run number, that means how many number of runs have been made and what is the best run. Then you can have 13 metrics here, product, compare, population, etc. Then finally you can have the range and best fit coefficient for that particular run. These are some of the outputs. How do you interpret the output? With the help of a legend that is already given. So this particular model was run for Chandigarh, and these are the results which we have obtained for 2030. So you can observe we have spreading kind of growth in Kharar region. If you are very familiar with Chandigarh, Kharar is in the northwestern Chandigarh, which connects further to Ludhiana and other important places. Then you have diffuse growth, that means there is no connection between the old growth and these new growth. So this can be identified in areas such as Zirakpur and JLPL industrial area. Why diffuse growth happens near industrial area? Because as once you set the industries, suddenly there is a growth of urban region or residential region surrounding to the industrial area. This is very sudden because it was not earlier planned. Since the industry came, the residential areas are also coming up. So that is called as diffusive growth. Then you have something called as spontaneous growth in the northern part of Chandigarh, if you see, which connects to the Kurali region. So you can see some kind of spontaneous areas. So this is basically due to the new Chandigarh region, that is eco city is being planned there. And finally you can see the organic growth. Organic growth means it is definitely depending upon the transportation, that is roadways. So you can see Pinjore and Kalka region, and this is due to the tourist attraction of nearby Kaushalya Reservoir, and the connectivity of NH22 is also very good there. So let us see a sleuth demo now to understand how sleuth actually works. Um, so here if you go to, as I already mentioned, Sigwin is the interface. So this is the Sigwin interface. So you can give some basic commands which you are familiar in C programming. Suppose let us say I'll give pwd, that means it will give the print working directory. So the working directory is D drive. I have put one folder such as working folder March 2020, and then I have put something called as sleuth, and then there is home. So let us see the home structure basically. So if you see here in the home, you have, as I already mentioned, you have GD, which is responsible for GIF image directory. Then you have input, output, scenarios, and world GIF. So these are various different folders which are very important for running sleuth. So let us see what is there in input. So in input I have so many subfolders for various, if you want to do a lot of cities prediction you can do. I have done, for example, Hyderabad, and Chandigarh is what we are going to do today. Let us see what is there inside Chandigarh. I will go here. So here I have one excluded layer, hillshade layer, land use for two different time periods, 1999 and 2017. Then I have roads for four different time periods, 1990, 1999, 2009 and 2017. Then slope for one time period, and urban for four different time periods. So S, L, E, U, T, that is nothing but road, transportation, and H, that is hillshade. So I have covered all the layers here. So if you want to see this, you can just see here, these are the excluded layer, hillshade, Chandigarh land use. Land use you cannot see anything because this is in a grayscale image. And these are the roads you can see here. This is a road, road in 1990, 99 road, 2009 road, and finally 2017 road. Similarly you have hillshade, sorry, this is slope, you can see the rough terrain here. Then urban for the year 1990, urban 1999, urban 2009, urban 2017. How do you get urban? Urban can be derived from the land use images. You make 1 is equal to 1, that is urban is equal to urban, and star is equal to null. That means any other category becomes 0. So you get only pure urban maps as a binary map. And then you have seen all the different images. So this is about the input folder. Then input I have two folders, that is one is test and predict. Test folder is basically to test whether your data is correctly configured or not according to the standards, that is GIF image with a particular resolution and with number of columns and rows. If you want to see that, you can just go to properties. So here if you go to details, you can see dimension is 657 by 363. Okay. Similarly, if I go to any other random layer, it should be same. So details 657 by 363. Yes. If there is even one small pixel change, that is, let us say it is 656 by 360, it won't work. All of the pixels should be proper in proper dimension. Then similarly to the input, you have output folder. CDG test output, these are basically empty now. I will show you when it runs how it fills up the folder, and you have predict folder also. So let us see how to run this. I also want you to show scenarios. So scenario CDG test, this is for the testing. If you open this with any of the editors, I'll open this with Notepad. So you can see here it has around 13 different setting parameters. So first one is path name variable. Here you can set the input and output, then running status, and you have working grids, Monte Carlo iterations, coefficients. So here you can set the coefficients, and image start and stop date. So I have given 2026, that means I'm obtaining the model output till 2026. You can even specify 2040, it will model for 2040. Then here these are the input layers which are used that just now I showed you. Urban, roads, transportation, hillshade, excluded and slope. All these are put here. And finally you have color table settings wherein you can change different kinds of color, etc. Similar to the test, we have predict scenario file. So more or less the predict and test are same, but only thing is the output which you are going to get in prediction will be image output directly. So here I have given for 2040. So I want to see what are the changes that are going to happen for Chandigarh in the year 2040. And then we have other various layers here in proper format, so you can change this also. Okay, so this is about the scenario file folder. And let us see, now let us run the test, that is nothing but cdg test, and see how the output will be stored in this particular folder. So to run that, right now I am in home folder. So what I'll do is I'll navigate this to scenarios. So if you want to see scenario, it is in home, scenario, and these are the files. So what I'll do, I'll go to cd scenarios. So now it has come inside the scenario folder. So if you want to see these files here in the Sigwin interface, just give ls, that is list files. So if you give ls, it will show you what are the different kinds of files. So now we need to run a test. So how do I run a test? Before running test, I'll go to the output folder so that you can see how it saves. So here I'll give, so this means dot dot forward slash means one folder up. I'm going one folder up, and giving grow.exe is the main execution file, and next is mode, that is test, and next is scenario file name scenario.cdg underscore test. Okay, this is what I want to run now. As soon as I give enter now, all the file folders will be saved here. Just observe. So now the model is running, testing is running. So 4 Monte Carlo iteration it is completing now. After completing 4 Monte Carlo iteration, you can see the files have been come here. So basically when you run the test, it won't give you any particular output for a future year. It will just run for existing data. So we have data from 1990, it has taken from 1991 and it has given till 2017. So let us see how it has given. So if you see here 1991, 92, 93, so it has been calibrated for 2017. So these are just the test values, okay. These are very random. You should not infer anything upon this. If the test run has been completed successfully, that means our model has run properly without any errors. So now let us see how to run a prediction. So what here I am just going to prediction output. So here I'll give one folder up, grow.exe, and now the command will be predict. Okay, predict what? Scenario file, that is scenario cdg underscore predict. Okay, so if I give this, it will start running the prediction for 100 iterations. Why 100? Previously we saw it was only 4, so that can be set using scenario file. So here if you can see in the test I have given the number of Monte Carlo iteration as only 4. That is why it ran only for 4 times. So if I come for the prediction, here you can see the number of Monte Carlo iteration has been set as 100. Okay, that is why now the Monte Carlo iteration is happening for 100 runs. The model has already finished 99th iteration, 100th iteration is also running, and it has now finished the 100th iteration. It is complete. Okay, now let us go and see how the output files are saved in the output folder. So it started from 2018 because since our data was ending on 2017, it started predicting from 2018. So this is the 2018 urban, 2019, 2020, 21, 22, 23, like that we have prediction up to 2040. So this is how 2040 Chandigarh, that is a sample area that we have taken, looks. And based on this you can also obtain the statistics such as urban area extent, etc. Okay, so this is how we model the urban growth using the SLEUTH model. You can also improvise this model using various artificial intelligence techniques such as genetic algorithm or particle swarm optimization, etc. So basically these algorithms are used to calibrate the entire procedure of modeling and optimize the entire calibration procedure. So this is the end of the demo, and if you have any doubts you can ask me now. Thank you very much.